Hello, we're back. So this is some introduction to equilibrium Green's functions. So in this opportunity I will talk about a very important topic, which is called the Lehmann Representation. As in our last video, this is an spectral representation, and it will be useful for several kinds of things, but more importantly, it will give us a feeling of more or less what is a generalized way to calculate the density of states. And this is quite useful in many areas of quantum physics, mainly when you use the formalism of linear response, which we will go through in another video, but we will here in this series of equilibrium Green's functions now. So then what I want you to think about is this. Remember that when we talk about the Heisenberg equation of motion, we said that in the Heisenberg representation, an operator that has some arbitrary time dependence t is equal to e to the ih bar ht times the operator in the Schrödinger representation times this is e here, times e to the minus I over h bar ht. Now, in other words, what this is doing is that is evolving the quantum mechanical operator from some point t equal to 0 to just an arbitrary t. So this is what this is calculating, is the evolution of this a sub h from t equal to 0 to t. Okay, so more generally, for those of you who recall equations of state, remember that, for instance, when you have differential equations of the form x dot of t equal to some matrix A times x of t, see, and then in the same way you can evaluate the transition from x evaluated at t0 to x evaluated at t. Now this is an arbitrary time, this doesn't have to be 0, t0 can be anything. And when you do that, you just need a transformation which is called in system dynamics it's called the transition matrix, that will relay x of t and x of t0. So that matrix will tell you in which way your state goes from t0 to t. That means that that matrix contains information about the dynamics of your system, about velocities, about for instance, how long does your system take to reach an equilibrium point. This matrix is usually represented by phi of t comma t0, and this is just a transition from t0 to t. So now what we want to let's say express is that if we have a quantum mechanical operator, let's draw the time contour. So then let's say that you have your quantum mechanical operator evaluated at t prime, and you want to know what is like the evolution of the quantum mechanical operator at t. So that means that you have h of t prime, and you want to know what is h of t. You want to calculate this temporal evolution. Now, what quantum mechanics tells us in a similar way with the Heisenberg equation of motion as with the Heisenberg equation of motion is that h of t, h of t is equal to e to the I over h bar h t minus t prime a sub h of t prime e to the minus I over h bar h t minus t prime. So then this expression is the expression that we shall use to elaborate furthermore what we're going to do in this video. So this, for the case of t prime equal to 0, of course, just recovers the Heisenberg representation for Schrödinger operators. So, which had this form that we already mentioned. So this is just this for t prime equal to 0. Okay, so there's nothing new here. So now we recall the definition of the Green's function, the equilibrium Green's function in its retarded form is g retarded of I j t comma t prime is equal to minus I over h bar theta of t minus t prime expectation value of the anticommutator of ci of t, cj dagger of t prime, where c and c dagger, ci and cj dagger are annihilation and creation operators. Okay, so now what we're going to do is that we're going to replace the representation of ci of t in terms of t primes. Okay, so we will only be left with t primes here. So then, to do that, what we have to do is the following. So then we write minus I over h bar theta of t minus t prime expectation value of the anticommutator of e to the I over h bar h t minus t prime ci of t prime e to the minus I over h bar h t minus t prime cj dagger of t, and we have done nothing, just replace the representation of ci of t in terms of t prime. So now we have that done, and now what we're going to do is we're just going to resolve this anticommutator. So just recall that the anticommutator, let me write it in red, the anticommutator of B, A and B is nothing but AB plus BA. Okay, which then gives us the following. So this is minus I over h bar theta of t minus t prime e to the I over h bar h t minus t prime ci of t prime e to the minus I over h bar h t minus t prime times cj of t prime. I forgot the t prime here, sorry. So this is t prime dagger. Okay, now plus cj dagger of t prime e to the I over h bar ht minus t prime ci of t prime times e to the minus I over h bar times the Hamiltonian times t minus t prime. And then we close the expectation value. So this is what we got so far. We haven't specified how we're going to calculate the expectation value. That's for later. And then now I want you to recall the following: completeness relations in quantum mechanics. Completeness relations in quantum mechanics, and specifically in the Fock basis. It says that the summation over m of the ket times the bra of m is equal to 1. So then that means that if I introduce this term here in any place between operators or between an operator and the exponential of Hamiltonian, then that will do nothing, that will change nothing, and is tremendously useful to calculate stuff. So that's why we're going to use it. So then, let me, in red, I will point out where are we going to introduce this. So this, we will going to introduce this right here. Okay. And we will going to introduce this right here as well. Okay, so we're going to introduce this to completeness relations, and then we're going to elaborate from there. So then let me just erase this to not just create a mess over here, and then we're going to do it in blue again. So then this is equal to minus I over h bar theta t minus t prime. Expectation value of E to the I over h bar Hamiltonian t minus t prime Ci of t prime times E to the minus I over h bar h t minus t prime. Now let's do it in red. Here I introduce the summation over m of ket times bra, see, and then I multiply that by Cj dagger of t prime here, plus this, which is Cj dagger of t prime so what else? In red again we introduce the completeness relation, summation over m ket times bra, and then again we continue with this part of the terms inside the expectation value, which is E to the I over h bar h times t minus t prime. Okay, times Ci of t prime times E to the minus I over h bar h times t minus t prime, and then we close here. Okay, so now what we're just going to do some just algebraic operation here. I mean, not even algebraic, but just for simplicity, we're going to remove these summations with respect to m and with respect to m, and we're going to put them in the front of the operation. So that means that here we're going to have this summation with respect to m. Okay, so that's what we're going to have, and then we're going to write, let's change color to more or less if we're going to just go through this to see where we're actually doing important steps, I think that can be helpful. So then this is minus I over h bar theta of t minus t prime summation over m expectation value of E to the I over h bar Hamiltonian times t minus t prime Ci of t prime E to the minus I over h bar times h times t minus t prime times the ket of m times the bra of m times Cj dagger of t prime plus this is Cj dagger of t prime times the ket of m times the bra of m times E to the I over h bar h t minus t prime times Ci of t prime times E to the minus I over h bar Hamiltonian times t minus t prime, and we close the here we close the expectation value symbol. Now this is the point where we have to ask somewhat several things. I mean, I could tell you now that, for instance, this term here, let's do it in a different color as well. I can tell that this term here is just the bra times e to the I over h bar times the energy associated with this Fock state em times t minus t prime. Why? Because this state is an eigenstate of the Hamiltonian, which means that if I apply the Hamiltonian on this m, then I will get an associated eigenvalue. Okay, that's what that means. And then in here I will have the same thing, but instead of bra, this is ket, but it's exactly the same thing. So that means that for the one above, what we have is that e to the minus I over h bar h t minus t prime acting on the ket is nothing but e to the minus I over h bar em t minus t prime times the ket. Okay, so then knowing this, we of course could replace we can do the following. Let's do it just by erasing h to make things smooth. We erase this h, and in purple we just write here em, and here we write em. So that's, for the meantime, that's what we can do. Okay, and now the other thing we can do is actually, let me erase these things in green. So now we can ask the question, what else do we do, or how do we evaluate the expectation value? So then this is what I'm going to talk about next. So this expectation value, how we are going to evaluate it is in the using the thermal expectation value, which is the following. So if you have, let's say, the expectation value of A, and you want to calculate it in some at some given temperature, so what you do is that you say that this is equal to 1 over z times the trace of e to the minus beta h. So what does that mean? Or how is that equal to what? So this is 1 over z summation over n. Sorry, this is the trace of e to the minus beta h times a here. So the operator a. Okay. So summation over n of the bra of n of e to the minus beta h a ket of n. So this is what we're going to use now. Just please remember this formula, because I'm going to erase this formula just to have enough space to maneuver here, enough space to move around. So that's the formula of the thermal average. So I guess it's quite simple. Maybe, I mean, some of you might know it already. So that's quite known in statistical mechanics. And since we're doing another big step, so we're going to change color for, let's do it in red now. So this is minus I over h bar theta of t minus t prime. Okay, this is the summation over m, but now we have some n, so then we're going to sum here over m and n, and this is n. Now this is e to the minus beta h. See here, this is then times what? This is times e to the I over h bar h t minus t prime ci of t prime e to the minus I over h bar em t minus t prime this is times the ket times the bro, and let me try to write this more compact because maybe we will get confused. This is times the ket of m bro of m cj dagger of t prime. Okay, this is now, since this e to the minus beta h multiplies the full thing and there is a sum inside, there's this sum symbol inside the expectation value, so we have to repeat. Okay, we either have to repeat or just open here some parentheses, that's better, and then keep on going here, plus cj dagger of t prime acting on the ket of m times the bro of m times e to the I over h bar em t minus t prime ci of t prime times e to the minus I over h bar times h times t minus t prime acting on what? On the ket of m. So this now looks like something promising. Okay, so then that's what we're going to do at the moment, and then just know that this e to the minus beta h acting on this bro is nothing but e to the minus beta times en, and the same with this h here. If you just move it over, you will see that the eigenvalue here is en, and the same with this Hamiltonian here. When you apply it, or when you operate with this Hamiltonian, or with this e to the Hamiltonian on this ket state, then you will pick up the associated eigenvalue with that ket state, which is en. Okay, so then now what we can do, after just having performed all those eigenvalue operations, just we will remove this e to the minus beta en outside, and we just gather here. So here we have e to the I over h bar, or e to the minus I over h bar en minus en times t minus t prime. We can just factorize this very easy, so then let's write it down here. Minus I over h bar. Oops, I forgot something. This is 1 over z, so then I forgot here the partition function. So this is z h bar theta of t minus t prime summation over m and n e to the minus beta en. Okay, and then what we have here, we have so parentheses, we have e to the minus I over h bar em minus en t minus t prime. We have n ci of t prime m let me erase this and let's write it here a little bit down. This is times n ci t prime m cj dagger t prime. And who is this operator here acting on? There is a summation here, so this is not acting on this, but it's acting on what? Yeah, the problem is that I forgot this parenthesis here. So then this one here is acting on this ket n. But it's not obvious because I messed the parentheses, so I apologize for that. So this is the first part of this calculation. Now the second part is I just add a plus here. And then, so this plus, since is the second term within the parentheses, so what does the plus get? So then in the parentheses, outside the parentheses, we already have the e to the minus beta en. So then that's okay. But this will act on this bro. So then that means that the first thing that I have here is n cj dagger of d prime m. What else do I have here? This ci, because this exponential we will take out. So this the sandwich between m and n of ci of d prime. Okay, that's quite clear, I guess. And this times e to the I over h bar em minus en d minus d prime. Okay, and let's close the parentheses now to just avoid any confusion. Now this looks more or less like that we will be able to simplify it. So then to do this, just know that since m and n are dummy variables, and I have two terms because I have a plus sign, so I have this term here first, and then I have this other term here. So then in the second term, in the one in blue, what I'm going to do is that I'm going to switch these dummy variables m and n, which means that I will pick up a term of the form e to the minus beta em, because I will be changing m and n, and I will explain in a minute why am I doing that. So then this is minus I over z h bar theta t minus t prime summation over m and n. So since I change m and n, now this exponential here and this exponential here, they have the same sign. Okay, that's what's going to happen. So let me just write this summation in. This is more clear. M and n. So this is e to the minus beta en first times the sandwich between n and m of operator ci of t prime times the sandwich between m and n of cj dagger of t prime. Okay, plus e to the minus beta em times, since we change here an mm, so now this is an m, this is an n and m. So that's what we're going to write. So we're going to write m cj dagger t prime n ci t prime m, and we use parentheses here, and all of this we multiply by the exponential e to the minus I over h bar em minus en t minus t prime. And now what else can we note here? So then so what we can note is the following. So this thing here and this thing here are exactly the same thing, so then we will factorize it. That's one of the purposes of just changing m and n. So this is minus I over h bar theta of t minus t prime, summation over m and n. So we have e to the minus beta en plus e to the minus beta em. We had here the partition function, now we put it inside to divide both of these exponential terms. Then we have times n ci of t prime m cj dagger of t prime n times e to the minus I over h bar em minus en. Wait, I ran out of space here, like usually. Sorry about that. So times e to the minus I over h bar em minus en t minus t prime. Okay, so then this expression now looks like something. So then this here is just the population of state n. This is the population of state m. So then we can write that in terms of populations, which is minus I over h bar theta of t minus t prime, summation over m and n, rho m plus rho m, and ci of t prime m cj dagger of t prime, and times e to the minus I over h bar em minus en t minus t prime. Okay, so this is what the Green's function looks like so far. So we have to do something else, so we're not just done. So then this is as far as we can go with the just the Green's function gij retarded of t minus t prime. So now I'm interested in showing you just this trick of the Lehmann representation for the case in which I is equal to j. And what happens when I is equal to j? So when I is equal to j, so we have the diagonal element of the Green's function in its retarded version, so gii of t minus t prime, which is equal to minus I over h bar theta of t minus t prime, summation over m and n, rho m plus rho n. And now since ci and cj will be the same thing, so then you see that this thing here, this expectation value, is nothing but the complex conjugate of this one. So then what we have is just the expectation value of n ci of t prime m square times what? Times e to the minus I over h bar em minus en t minus t prime. Now we're going to assume what we discussed in the very beginning of the lecture, that t prime is 0. So what happens if t prime is 0? So if t prime is 0, so I write gii retarded of t equal to minus I over h bar theta of t summation over m and n, rho m plus rho n, sandwich of ci of t prime between the bro of n and the ket of m, all of that square, so that's a probability, times e to the minus I over h bar em minus en t minus t prime. Okay, so then what we're going to do now, in order to achieve a spectral representation, is that we are going to express theta of t. Let me write it in red. We're going to express theta of t using its Fourier representation, which is minus 1 over 2 pi I integral of minus infinity to plus infinity e to the minus omega t d omega divided by omega plus I eta. Okay, so then what happens if I replace that here? So how does the Green's function now look like in purple? Let's change again. GII retarded of t, it will be minus I over h bar times 1 over 2 pi I minus here integral of minus infinity to plus infinity here of e to the minus I omega t divided by omega plus I eta d omega, this times the summation over m and n, rho m plus rho n, okay, times the sandwich of ci of 0 between ket n and bro n and ket m all square times e to the minus I over h bar em minus en t minus t prime. Okay, so then what we're going to do is this. So first, this minus I goes with this minus I. So that's the first thing. Let's just write it down. 1 over 2 pi h bar. Done. Then we're going to move out everything that has to do with m and n that has nothing to do with time. Okay, so then this is the summation over m n rho m plus rho n and ci of 0 m squared. That's why we set t prime equal to 0, and then we multiply this by the integral from minus infinity to plus infinity of e to the minus I omega t times e to the minus I over h bar em minus en. Oh, this t prime here was 0, of course, sorry. This times t d omega divided by omega plus I eta. Okay, so there is so the people usually, when you have this in terms of the occupations, they will call this the Lehmann representation. See, but the Lehmann representation itself, it's a spectral, so it's a spectral representation. So actually people can call this Lehmann representation, but that's not what Lehmann representation is. You need to have a spectral representation for this to be the Lehmann representation. So we're not there just yet. So then this is 1 over 2 pi h bar summation of m n rho m plus rho n, this probability amplitude square, so that's a probability, ci of 0 m all square. Okay, and now here what we do is just we gather similar terms in the exponentials, and then we say that this is e to the minus I over h bar of h bar omega plus em minus en times t divided by omega plus I eta all d omega. And then here we made the following change of variable. If we have h bar omega plus em minus en go to h bar omega, so what will happen is the following, is that our new representation looks like 1 over 2 pi summation over mn. I will tell you what did I do with the h bar, rho m plus rho n. The sandwich between the bro n and ket m of ci of 0. See? So then all of that square, which makes it again a probability. Then this integral now looks like this. This integral looks like to minus infinity to infinity e to the minus I omega t d omega, and downstairs looks like h bar minus em plus en plus what do you call plus I delta, which is a new variable. And what I did with the h bar here was the following. So look that here downstairs I just had the omega, so then this h bar came here to multiply omega and to multiply eta. So that means that delta, the new delta, is nothing but eta times h bar, and since h bar is small enough to make eta even smaller, so delta is super small, so then we can do that. And in that way, when we have here h bar omega, then we can perform this change of variable in terms of h bar omega. So that's where the h bar went to. So now we will have this, and then we can write the Green's function in the following way. So then since g, or let's use any function f of t. So f of t is equal to 1 over 2 pi, the integral from minus infinity to plus infinity of f of omega of the omega. So whatever is inside that integral is g of omega. So, and since this does not depend on omega, so we just put it inside. So then from this line of argument, I can say that gi of retarded of omega is equal to the summation over mn of rho m plus rho n. So bra ci of 0 ket m, all that square, and all of this, sorry I forgot here, so this is just in the Fourier transform, this is e to the minus I omega t d omega. Okay, so then, and here going back to the spectral representation, so this is h bar omega, see, so minus em minus en plus I delta, and this is the Lehmann representation for the Green's function in retarded version. And now, why is this important? So this is important basically because of one thing. So from here, from a very intuitive form, you can derive the density of states. Okay, this is now a full spectral representation. We can call this the Lehmann representation, and then we can ask ourselves, where is the imaginary part of GII, retarded of omega? So then what we can see is that everything on the top part of the fraction is real. This is a probability, that's real. This is an occupation, is real. This is another occupation, is real. So the only source of complex numbers that this expression has is its denominator. So that means that the imaginary part of the retarded Green's function II of omega has to be something like this, equal to the summation over mn rho m plus rho n bro n ci of 0 m square times the imaginary part of 1 over h bar omega minus em minus en plus I delta. Okay, so then, and the imaginary part of this we already know because of one of our previous videos. So then the imaginary part of this is nothing but minus pi delta of h bar omega minus em minus en. That's what the imaginary part of that is. Now, I want to convince you that from the Lehmann representation I can derive an intuitive form of density of states, and this is what I'm going to do. So then, if this is the imaginary part of GII retarde, so then what would happen if I ask what is minus 1 over pi, the imaginary part of GII retarded of omega? And this will be nothing but the summation over m and n rho m plus rho n and ci of 0 m all square times delta of h bar omega minus em minus en. And then my claim is the following: this expression is a generalized expression to calculate the density of just a single state in the many body pictures. This is a generalization of the many body density of states. And how we can see this? The following way: these states m and n are the many body states. So that means that em and en are eigenvalues of the Hamiltonian H, that is an eigen operator to the many body state M. Okay, so these are many body states. That's very important. Let me put it in words. H on M has an associated eigenvalue Em. Sorry, this is M here. And this eigenvalue associated with this operator H is the eigenvalue of the Hamiltonian when the Hamiltonian acts on this many body state. So this is a many body Hamiltonian. Okay, so then I'm not saying that it's an interacting Hamiltonian. I'm saying that it's a many body Hamiltonian, which is a different story. Okay, so then now what we can see is that level I, here represented by this operator ci of 0, we need to know what are the population between any two other states. Let's say em and en. Just know that when em is equal to en, so then you just basically have 0 here, because then the condition is that h bar omega is equal to 0. So that's pretty much we're just at 0 energy in that case. So then we require for em and en to be different. And what this says is this: what is the probability for you to go between any state I? So you have I here, the annihilation operator for I, and this nm is the probability, so is the likelihood for you to go between n and m passing through I. Okay, so this is the projection of these many body states onto the state I, and then that response only triggers when the difference between the levels from which you are populated I coincides with some drive h bar omega. Okay, so then this can be seen as a generalization of the density of states, and that's why you usually will see in equilibrium, this is very important, in equilibrium, that d of omega, since this is just for a single level I, so then this is the single level density of states. And if you want the many level density of states, that means that you will have to sum over I here, which is equivalent to taking the trace of G of the matrix G of omega. Okay, there is no I here because this is a matrix now. So then, and that's why basically you will see that the density of states in equilibrium is usually expressed as minus 1 over pi times the trace of the imaginary part of G retarded of omega. Okay, so this is more or less a generalized form, or generalized form of the many body density of states. It's a very intuitive way to get here through the Lehmann representation. So I will repeat once more. You have this delta that will impose a condition on the system that for you to populate a given level, so you need to drive. You need that your frequency drive, or that your energy that you're input in the system to populate a given level coincides exactly with the difference between two levels from where you're populating. You need to know the population of each level. So I mean, these levels need population. They have to be populated, and in that way then you calculate the density of states of level I associated with the destruction operator Ci. So then this, of course, with let's say a little bit more of thought, is seen as a generalized way to describe the density of states, the many body density of states. I will upload a different video where I actually go a little bit more over this concept of generalized density of states, but for the meantime, what you should remain with is this formula. So this formula is extremely important to calculate density of states. We will use it a lot, and then we will extend it to the non-equilibrium case, which is what concerns when we have systems that are biased by voltages, where you apply temperature differences, where you apply very strong laser pulses. So then that will come in another opportunity, and for the meantime, I hope you have enjoyed this video, and just remember the take-home message, the Lehmann representation, and the generalized density of states. Thank you.